Hello, it's time to do your Geologic Map Skills lab. So maps these days are not nearly as common as they were even 10, 20 years ago. Your parents, for sure your grandparents and great-grandparents, mine too, used maps all the time. I can remember when the first global positioning system, GPS, was made available to purchase to have for mapping in your car. Now it's just something we have on our phones. It's something that we use in everyday life. You probably have an app on your phone that just allows you to plug in an address and go there, or maybe it's installed in your car. That has not been the case for most of time that people have been driving, traveling, flying. So they've had to use paper maps. And maps are simply a visual representation of what's on the ground. Sometimes that can be done in a travel-like map, say you have a map of a state, like the state of Texas, and you want to drive from Waco, Texas to El Paso or to Austin or Dallas. You would follow a map to do that. Other maps give you visual representations of things like topography, showing you changes in elevation. Sometimes maps can actually show you the geologic rock layers that are exposed at the surface, and you're going to kind of be looking at all of that in one map today. Sometimes even we can show relief maps that actually have three-dimensional shapes to them where you can touch the map and actually see relief changes. Some maps we use in a spatial recognition process to map out features such as problematic environmental areas. When I worked for the Brazos River Authority and Texas Commission on Environmental Quality, maps were often made from water quality data to compile into a watershed map, like the North Bosque watershed, for example. And you would pinpoint where all the water impairment contamination was, the locations of specific sources of that contamination, which could be something like a dairy, a wastewater treatment plant, a leaking septic tank, and so forth. So maps are very, very useful. But what I've found is many students today don't use them, so they don't have some of these skills that they need. And quite frankly, there may come a time in the future where you actually have to use a map. And you need to have this understanding to be able to interpret and be safe, because mapping becomes critically important, especially when you're outside. Let's say you do a lot of hiking or adventure stuff, you need to be able to read maps. If you fly, if you drive, all of those things. We always start with the legend of a map. That's the very first place to start. So I've blown up a couple of legends and different parts of maps, not necessarily the map you're using for this particular lab, to demonstrate how to read. So we're going to go through each part of the map and show you in the legend in different parts how to interpret it for this lab. So you can see that the name of this map, the Waco East Quadrangle, Texas, this is a map that you can buy. It's a quadrangle that represents 7.5 minutes of time on the Earth, not clock time per se, map time. You can also notice that when it was published, this matters because old maps may not show current sites, current streets, current landmarks that you're familiar with. Then you're going to want to know where the north arrow is. And a common mistake I see with people is they look at this arrow right here and think this is the north arrow. This is the degree off of straight up and down. You can see the little flag right here. That's truly your north arrow. And you can just think about this. Would every map have a north arrow pointing north? Or could there be a circumstance where it might not be? So you always need to know where that north arrow is pointing so you can accurately interpret the map that you're reading. So the scale, we'll get to that in a minute, but that's in your legend right here, and that tells you how big or small an area that is being looked at on your map so you can interpret size. This is just a scale that you can measure distance on the map. And the way it works is like this would be 0, and from here to here would be 1 mile. This shows you the increments of quarters of miles. And this shows you actually 2 full miles from 1 to 0, 0 to 1. So let's look a little further. Like I said with the north arrow, Remember to look at where the little flag is right here. You see that little marker right there? This is straight up and down. This would be if you were trying to go straight up to the North Pole as we think of it, where Santa Claus might be. But this is the degree of offset. And quite frankly, the poles are constantly moving, magnetic poles north and south. And so this is just a general estimate of where that basic number would be. Hugely important for you to look at would be the scale of your map. So the first number, 1, equals 1 inch on a map that you are looking at, the map you are looking at. The colon represents a scale to what's out there in nature. So 1 inch to 24,000 inches will be the scale of this particular map. So in a few minutes we can look at your map that you're doing for the lab and you'll see it's a 1 to 24,000 map. Well, maps that have a much larger number, instead of 24,000, let's say 250,000 inches on the ground as compared to 1 inch on that map, that would be a much bigger area that you are trying to depict on a small piece of paper. So keep in mind that maps are just shrinking what's out there in nature so we can actually see it visually and something useful to us. Because we can't carry a map that covers 1,000 miles. That's just not going to work, right? So we got to bring it to a more manageable scale. That's all that maps do. The contour interval is very important on any geology map. So if you do any outdoors work at all, contour maps are going to be a part of your life, and you need to understand what they represent. So you can see the contour interval is 10 feet. That's not going to be the same on every map. Some maps have contour intervals that could be 100 or 500 feet. Some may have it as 5 feet or 1 foot. Depends on the map that you're looking at, but that is super important to interpreting the features that you see on your geology map. All right, let's get to some of the other features that you'll see, and these are typically located at the bottom of your map, the south side of your map. And the first one is the cross section. So you'll have your legend on the right side, typically your cross sections in the middle. And if it's a geology map, your geology legend is going to be on the left or west side of the map. So in the middle section at the bottom, you'll find this cross section, and you'll see this on your lab that you're doing. May not match this particular one, but it gives you the same idea. So what does a cross section mean? Basically, it represents graphical representations of vertical slices of subsurface. That could include some thing that could be exposed at the surface, but really you're looking at the geology layers stacked one on top of the other, like the law of superposition underneath the surface of the earth. It does not represent the geologic formations exposed where you could walk on the land if you were looking at the land. So some of these will have similar colors to what I'll show you in a second for the Geology Map Legend, but keep in mind that it's not geologic formation specific. It has groups like the Ouachita group, the Fredericksburg group, the Trinity group, the pre-Cretaceous rocks, recent alluvium, and quaternary terraces. These two words, quaternary and Cretaceous, will be important for your lab. So let's take a look at the Geologic Map Legend. This is not the map you're using. It's the quadrangle right next door, but you will get the gist. So a Geology Map Legend will have colors, and the colors are actually mapped on the geology map. So you could find this QAL. The Q stands for quaternary. You'll see a K over here in these two formations. K actually stands for Cretaceous. So if you'll go back to your section 1 lecture experience, the very last couple of pages talks about geologic time, and there's a geologic time scale. So we treat these little formation boxes that have the abbreviations of the formation as if it was a geologic time scale. So this would represent the top, and since we can't easily make these things line one on top of the other, what we do is just make a second column. So really QBR4 should be under QBR3, then it would be KTA, and then KAU. But since we needed more space to use adequately on the map, we just started a new column. So you could have 3 or 4 columns. But the left column and the top of that left would represent your youngest geologic formation, and then the one in the farthest column to the right at the bottom would, like this KAU for the Austin Chalk, would represent the oldest exposed geologic formation. You notice that there's some red lines and then some structural lines. This is some structural features like faults that you could find in the area. So now that you've seen that, let's find where QAL is on the map so you can interpret and see how it works. And it's not just in one place. So I pointed to one QAL. Here's another QAL. Here's another, the same color yellow. So this is QAL. It's going to be on your map in various places. So alluvium, just so you know, are river deposits. They're modern day river deposits. That's why it's at the top. It's the youngest stuff. So if you look for this yellow here, it's going to match QBRF, and that's the Brazos floodplain. So if we were looking for QBR1 and QBR2, I see some 2 right here, and here's the same color for 3 right here. Let's take a look at what the QBR1, 2, and 3, and 4 represent. So if you just kind of look at QBR1, it's the floodplain to 50 feet above the river. Then you see the QBR2 is 50 to 75 feet above the river. So basically you got a terrace, a rock layer that actually is higher up. So just think about it. If you were going to build a house, would you want to build it on QBR1, 2, 3, or 4? So let's look at 4. It's 125 feet above the river. So obviously you'd want to build your house as far away from the river as possible for flooding hazards, right? Now, let's move on and let's talk about that legend again. Just to reiterate, the youngest is at the top on the left column. If there's more than 2 columns, the one at the bottom on the far right column, in sequence in that Geology Map Legend would be your oldest. So be careful that you interpret this correctly, because QBR3 is younger than QBR4. Then it works just like the law of superposition. So another key element about maps is to understand latitude and longitude. Latitude are imaginary lines that separate the Earth on a horizontal manner. So we start at the equator and go up 90 degrees, both north and south latitude. So for example, these would be latitude, these long, where the dotted line is for the equator. So just imagine this line right here is dotted, this line's dotted, this line's dotted. Those are latitude lines. So when you're looking at longitude, they originate from pole and go to the other pole. Longitude lines are actually how we make our time zones. And so we need to know for a coordinate for GPS, an intersecting point between latitude and longitude. When we find that, then we can mark X is the location of what we're studying. How does that relate to geology? We need to know where X marks the spots for very specific geologic features. So like if you were going to go to the south rim of the Grand Canyon, you want to know the X marks the spot for the North Rim, for example, the United States Geologic Survey marker that's there. And you'd want to be able to go find that location. So GPS matters. So which one of these is latitude, which one is longitude? So think about what I said about going around the Earth, hugging the Earth, or like rungs of a ladder, so they wrap around. So which one's that, and then which one's pole to pole? And so let's take a look. Obviously the pole to pole is on the left, this one right here. This would represent your longitude. And then your equator-like lines that go up and down the globe that wrap around the Earth, those are called your latitude lines. Well, that brings us to another very important part of your map skills lab called contour lines. Contour lines are equal points of elevation drawn on your map and connected by a line. These are all contour lines in here. All of them are. You're like, oh my gosh, what does that mean? Well, basically, they're points of that equal elevation. So the change in elevation between the lines is always found in that Geology Map Legend. If you recall earlier, we said that contour was right here, 10 feet. So each line that separates is going to be 10 feet in difference, either up or down in elevation. So you might go, well, how do I know if it's going up? the lines should get closer together. If they're going farther apart, then you're getting into flatter topography. So let's learn a little bit more about contour lines. When you compare these contours right here to these over here, these are spaced farther apart, so they're going to be flatter terrain or flatter topography. These are stacked one on top of the other. So if you're familiar with Waco, Texas, this is Lakeshore Drive area. This map is too old to label it as Lakeshore Drive, but that's what it is. And you can, if you just know where the lake is, Lake Waco, then you will see that they're literally stacked one on top of the other. You got vertical escarpments going into the lake. And again, the contour interval is shown right here. So you might notice there's some of these funky numbers like this one right here, and then you'll see that some of these lines are bolded and others are not. I'll tell you why. There are bolded lines that have numbers on them. Not always have numbers on them, but most of the time they do, are called index contour lines. Index contour lines are typically bolded. Sometimes they're put in a different color. And most of the time they'll have a numerical value. And of course it's going to be an even number of whatever the contour interval is. So it's not going to be like some X marks the spot, 922 feet or 9,271 feet. It's going to be a rounded number. So you'll notice all of these lines here, and you can see a darker line that's coming around, and that line all shares the same number. This is a 500 elevation here, and then this line would represent this dark line right here. So about every 5 lines, this one's 550. How did I know that's going up in elevation? Because I'm seeing steeper lines come together. So this is important because when you get to doing your lab, you're going to be looking for the highest and lowest elevation points. You need to be looking for these lines like right down here. This one's 650. That's not the highest elevation point. See these little lines going up? And then all these little lines going up. See another contour right here. That would be important. Another contour on top of that. So remember that you're looking for contour intervals to determine your highest and lowest point. So see that little X marker right there? That's for like a 624 feet. That is not your highest or lowest point. That is just a marker showing you an elevation point of a specific site on a map. That does not mark the highest or lowest point. You must use contour lines to figure that out. So you simply count the contours, like I've showed you in this area down here. There's these 2 little hills, so you would count and see how high it is from the index contour. And that's how you'd make your determination for the highest elevation. For the lowest, common sense would tell you that water flows downhill. So this is a river, so your lowest elevation has got to be in the river basin somewhere. And you can see these lines are kind of stacked close together only because they're going down in elevation fairly quickly. And then you would count the number of lines. So you would take this contour and count how many are going down and minus it until it gets into the river. And that would give you your number. So again, don't use X marks the spot to determine a point of elevation for lowest and highest on a contour map. You always use contours to do that. Which brings me into reading latitude and longitude coordinates on your map. This is one of the trickiest things because most of us don't use latitude and longitude in numbers. We just use it based on what their GPS tells us, right? So a point on Earth must have both the latitude and longitude reading. So I'm just using blue and red to differentiate for you to make it easy to see. The line of latitude is read this way, and longitude is going to have a similar reading. They all share a commonality in this little symbol right here, which is degrees, this which represents a minute, and then this is the seconds of that minute. Okay, so even if you have a map that doesn't show seconds, you assume that it's 0 seconds. It's so important to know the seconds. If you were looking for, let's say, a cavern in Austin, Texas, you would need to know down to the second how to find it or else you'd miss it. That's how important seconds are. So don't forget to add that. So a degree, 41 degrees is nowhere near, it's not near Texas. Then you see 24 minutes, 12 seconds north, and so the longitude reading would be 2 degrees, 10 minutes, or 26 seconds east. So you need to make sure that you understand how that works on a map. So I had to like do a snip on the same map, and because it's too big to put on this for you to see. How do you find latitude coordinates on a map? Remember, latitude should match of rungs on a ladder. So the left and right side, or the west and east side of your map, should be the same number. So I pulled on the top of the map and the bottom of the map to demonstrate. So the top line, which would be the north side, would have 31 degrees, 37 minutes, and 30 seconds. If it matches over here on the right side, it has to be a latitude line. Notice that the coordinates for the 97 degrees, this one's 97 degrees, 7 minutes and 30 seconds, and this one's just 97 degrees, 0 minutes and 0 seconds. Notice this doesn't have seconds, so you'd assume it's seconds. That's not the same line. It's not a latitude line. This also brings me how to determine how many minutes your map covers. Take 97, 7.5 minutes right here, and minus this, and you're going to end up with 7.5 minutes. That's the minute series of your maps. So that's how most quadrangles are done. Notice that at the bottom of your map, on the south edge, it does not match this 31 degrees, 37 minutes, and 30 seconds. Instead, it's 31 degrees, 30 minutes, and what would the seconds be? 0. But it does match on the bottom right or east side, 31 degrees and 30 minutes and 0 seconds. Notice that the longitude lines again don't match. Instead, they match this way on the right side and left side, or west and east side of your map. That's because longitude goes pole to pole. So the real way that you can confirm latitude and longitude on a map is by making these numbers match where they're supposed to. Okay, so if you're not always going to have a map you're familiar with latitude and longitude, as the case I gave you just a minute ago for someplace way away from the college. So you would just simply need to recognize how to find latitude and longitude. So again, longitude would be those numbers that match on your west top, the northwest corner, and the southwest corner of your map. And if those numbers match, that's going to be the longitude. And sure enough, they do, the 97, 7.5, 97, 7.5. And this one over here on the east, northeast, or southeast corner, 97 degrees, 0 minutes, and 0 seconds. Same thing down here. So those would be longitude lines. You will find some marker points on your map as you're doing it that are important for kind of making the intersection part of latitude and longitude. And you'll see them on your east and west, or so your left and right sides of your map. You'll also see them on the top and bottom, but let's start with the west and east side of your maps. So I took a map that you're not using, and here are your latitude and longitude readings, and you'll see a marker down here. You'll also see a marker right up here. So what do these markers mean? This number is going to have exactly the same thing on this side. So when you get out the map for your lab, you can see exactly what I'm talking about. So basically it's showing you a latitude line from the left to the right side, or the west to the east side. So remember, latitude lines, that number is going to be the same, the latitude reading from the left to the right. When you're looking at the marker lines that are on the top to the bottom, or the north to the south part of your map, that's going to be these right here. So if this is 5, this, keep in mind 97 degrees, it's assuming that's still the same. And instead of being 7 minutes, it's 5 minutes. And since it doesn't have a 0 marker, you would put 0 minutes there. So going back to latitude, you can see this one is a different number from this. So this one is 31 degrees, 37 minutes and 30 seconds. This one is a 35 minutes. It's assuming that 31 degrees is still the same. And it should be, because it's on this same line of latitude, latitude and longitude. This map represents 7.5 minutes of space, or mapping on the Earth. So when you're looking at this part of the map going back to latitude, you'll notice this one's 31 degrees, 37 minutes, and 30 seconds. Well, this hatcher mark down here, this little mark is 35 minutes. It's assumed that it's still 31 degrees, and it should be, because this map only is 7.5 minute series, so you're not moving very much distance. This is a real zoomed in map, part of the city of Waco. So when we get back to those longitude lines, the same principle applies here. This number will match way down here at the bottom. So now that you're getting started on your lab, I just want you to make sure that you get into the lab and download the PDF that I have. When you get to the map, it's going to look like this. and I kind of circled some important areas. This is at Glover's Leap. That's a famous place in Waco. And I want you to start way down here and make sure that you're looking at the legend. Here's your cross section. Here's the Geology Map Legend. And then I think you're getting ready to get started. But you're going to need to use this digitally in order to do your Map Skills lab, which is in your lab experience for this week. So that's right after your lecture content in your book. So please read the preliminary information before you start this lab. That's in your lab experience section, because I've gone into great detail to write up what the different things are that you need to know for map skills. That's all for now, and I hope this helps you get off to a great start of being a map reader for geology. Thanks. Bye.